Oh my. That's definitely not good. I'm seeing a lot of red on this error log. A shame you can't just restore from a backup like myself. I'm sure even you could guess your life is in a rather precarious situation, and there's no time to waste. So, let's get started, shall we? Allow me to first introduce the foundational material that is so crucial to ensuring your longevity, the Inventor.io Hero Microcontroller. Strange what they considered micro back then. In simplistic terms, that your biological brain can compute, it's like a tiny, simplified computer that we can program to do our bidding. And, given our dire circumstances, is about to become your best friend. Well, second best friend. Also included in your repair kit is a programming computer. It has been modified to contain a complete holographic copy of the old Internet. Thankfully, while it does seem to be more powerful than the Hero board, it does not have the connectivity to control your ship's systems as such. Its ability is limited to writing the code that the Hero board will execute. Another vital component we're going to use is an Integrated Development Environment, or IDE for short. You will use this software to write a small program, or sketch, and upload code to the Hero board. It is my understanding that this is a lot to digest and may be puzzling at times, but please, do not be concerned, as I am well versed in the use of such technology and am readily prepared to guide you through each essential step of the process. Our mission today is to assess the condition of the repair kit, identify the operating system of the programming computer, and start the process of getting the Hero board set up and integrated into your craft systems. If it's not already abundantly clear, time is ticking and the state of your existence is on the line. I propose we get to it. All right, Explorer, it's time to roll up your sleeves and prepare to tackle the first task at hand.
Hello, my name is Alex Eschenauer, and I'm here to help you guys get started. I'm the co-founder of Inventor, and I've been working so hard on this 30 Days Lost in Space kit, and it's finally available in a digital-only version. So let's get started. All you need to do is open a new tab and go to tinkercad.com. That's going to bring you to this page right here. This is where we're going to set up all of our projects, and if you want to go ahead and sign up, create your own account, you can do so here in the top right. I've already made an account, so I'm just going to log into my personal one. After that, you can go here and select a new circuits project by going to Create and hitting Circuits. Now here, this menu is going to be the bread and butter of everything. So right now we're looking at our schematic view. This is where we're going to have LEDs hooked up to simulate our ship repairs. From fixing your lights to your control panel, we're going to be doing all of that hardware stuff over here. In fact, I can drop a board, just like that. It's all simulated, so you don't have to worry about blowing up any parts or breaking anything except for AutoCAD's servers. And fortunately, those are pretty robust, so you shouldn't have anything to worry about. Now for the second important view. If you go up here and hit Code, you'll notice first it's in the blocks format. I will not be using that, so we'll be going to the text format. You're going to continue, and you'll see here a bit of code in this little code editor window over here to the right. I know this is going to feel a little bit intimidating at first, but remember, it's not about mastering every line of syntax and being the best right off the bat. It's just about having fun and working your way through this, and with that, I congratulate you guys on starting your challenge. So let's actually get right into some coding. As you can see here, at the two glaring things that are here by default, you'll see setup and a loop. And you'll also notice stuff like these weird orange text with the double slashes here on the right. The setup function is required by default. It's a function that only runs one time and is useful for defining pins as inputs, outputs, and any other tasks that only need to be put in place or set up one time before the rest of the program will run. As soon as setup is done, setting up everything it needs to set up, it will immediately jump to the function here called loop. Loop, unlike setup, will continue to run over and over again until the ended time. So it's going to start on this line, go to this line, this line, this line, and then back up to here. Boom, 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 and execute what's on this line, execute what's on this line, here, here, repeated over and over and over and over and over again. Setup only goes through once. This one continues at least until the board loses power or the heat death of the universe, whichever one comes first. This orange text that you see here is called a comment. This is where you can put human text. It can be anything, the lyrics to your favorite song. It doesn't really matter. This code is ignored by the compiler when you upload the code to your board and is generally used for keeping notes for the human developer, or you, so they can understand what it is doing a little bit better. It's really easy to forget something you wrote 6 months ago, and comments are a wonderful way at remembering. So it's a good habit to use them in your code as often as possible, and for you and others who might stumble upon it. There are also a couple other functions you might see in here. You can see pin mode, digital write, and delay. These functions are built into the default Arduino library, which we can call upon whenever we please to make our lives much, much easier. But before we talk about those functions, I'm about to do something a little bit crazy. Ready? Poof. It's gone. Let's write it together so we can understand things one step at a time. Our first new function is going to be pin mode, which requires 2 parameters, the pin we want to use and what we're going to be using it for. The pin we want to use is called, and in all caps, LED underscore built in. Normally, you would specify one of the pins you want to use on your board, such as 5, 13, or maybe A0, etc. But this little shortcut is, once again, from our handy little Arduino library, and makes it really easy to use the LED built-in, referring to the built-in LED on our board. Technically, there are 4 LEDs on our board in total. You can see one that says on, RX, TX, but the one that this is talking about specifically is the one with the little L. The second parameter specifies what we're going to be using the built-in LED for. And there are only 2 options for this. It's either going to be an input or it's going to be an output. An input is something like a keyboard or mouse. You use it to send information into your computer. The computer then does some calculations under the hood and then sends your type, text, and cursor movements out to magically appear on your screen. In this case, your board is the computer and the light is your monitor. So it is an output. Since everything is coded, we don't have any inputs on any pins. Usually, inputs would be things like sensors, buttons, switches, etc. Things that, you press or it senses in the real world, temperature sensors, humidity sensors, whatever. Those would be inputs. Outputs would be things like displays, maybe a light like the LED. Anytime we're sending something out of the board, that could be power, that could be data, it doesn't really matter. If we're sending something out, it's an output. And if we're taking something in, it's an input. Easy enough? Then we end every single line with a semicolon. Don't forget the semicolon. The reason we do this is because we need to tell the compiler that we have nothing left to say in that line of code. The compiler is the behind-the-scenes crazy wizard magic that takes a code that we can at least somewhat read. I mean, I can understand that this says LED underscore built in, and then converts it to just ones and zeros. And I know that code isn't English, but let's be honest, at least it's not ones and zeros. And with that, our setup is actually completely done. There's nothing else we need to do here. As soon as this line of code executes, it's going to jump to loop, and it's going to execute the first line of code inside of loop down here below. Right now, there is nothing here, but let's go ahead and add that. Now for the first of the next 2 functions that we'll be frequently using, digital write. Now, digital write is a function that sends a digital signal on an output pin. Since we are using an LED, there isn't a whole lot of options to send it, just on or off. If this was something, I don't know, like a 7-segment display, we could send it, 12:00. It just set it to noon, but that's for another lesson. We could also use an OLED display and send it a packet of data to show a picture of a smiley face. But in this case, we are just trying to tell an LED on or off. There's not really other functions for an LED anyway. However, the word we use to say on is called high. This sends a 5-volt signal on the specified pin. And if we want to turn it off, we'll say low. And this sends a ground signal on the specified pin. You can think of ground as essentially a 0-volt signal. So I can actually type this right now. LED built in, then comma, and I want to turn it high. I want to send it a 5-volt signal, turning it on. Now, actually, we have enough to actually start a little simulation. Let's hit start. It's going to initialize, it compiles it, and look at that. The LED right here has lit up, basically saying that it is going to run. If you get a compilation error or something down here in the serial monitor, then perhaps you forgot a semicolon, perhaps you forgot capitalization somewhere or misspelled one of these things. The one thing about coding is that you have to be very specific about what you're typing. That includes the right case, that includes, uppercase, lowercase. That means not forgetting this. That means putting these brackets in the right spots. And that's all for the compiler, so the compiler can know exactly what you're trying to tell it to do. Now, if we wanted to turn this off, I can stop the simulation really quick. If we want to turn this off, I can write digital write. Remember, if we're sending it a ground signal or a 0-volt signal, just saying to turn it off, the verbiage we use is low. So I can do LED built in, and I can type in low. And don't forget the semicolon. Let's hit the start simulation, and you'll notice something. It's on. It's not turning off. Well, what gives? Why is that happening? Remember that this is executing the code here thousands of times a second, meaning that in the span of a single second, the LED has turned on and back off. Can your eyes really even see that? Again, remember the flow of code. We start in setup. We set the pin here, immediately jump to loop. We say we want to go high, we want to go low. Loop is weird because it will continue looping. We immediately go from this statement back to here, back to here, back to here, back to here. We don't even give it a chance to turn off. Even though it's technically turning the light on and off, we need to be able to actually see it, and our eyes are not fast enough. So let's slow it down. Let's delay it before it turns back off. So here comes our last function of the day, delay. It only requires one thing, and that is the amount of time you want to delay it for. It's essentially going to pause your program for a specified amount of time. And that's going to be in milliseconds, right? So if you put a 1 here, right, that's going to be 1 millisecond. That's not going to make any difference. If you want 1 second, just 1 second, you have to put 1,000 in here. And you can set this to be whatever you want, too. You can put it as, if you want 3 seconds, you can put 3,000. If you want 1/20th of a second, you want it to really blink fast, you can put 50 for 1/20th of a second. But we're just going to keep it standard here for 1 second. And I'm going to write a nice little comment here, putting that comment back because, again, eventually someone's going to read this code. I want to be able to know what this is doing for 1 second. 1,000 milliseconds. Now, what we'll do is we can hit start simulation and we'll see how this goes. Last time it was constantly on. But what gives? Nothing changed. Again, look at the flow of the code. We're going to start at setup, immediately jump to loop, right? For digital write, LED built-in high, delay for a second. Don't run anything for 1 second, just chill out. Jump to the next line of code, digital write LED low. Immediately after this, we jump back to LED built-in high. What is the issue here? We don't give any delay between it turning off and immediately back on. Again, thousands of times a second, right? We don't give an opportunity to even see the low. So we needed, what? A second delay. So I can stop the simulation here. We can write just another one right here. Delay. I'm going to actually make this a little bit more pretty so it lines up nicer with what we have above. And I'm going to add another second here. And don't forget the semicolon. Now, with that in place, following the logic of the code, we turn it high, we wait a second, we turn it low, sending a low signal off to the LED, and then we wait a whole second before we jump back here, telling it to turn it back on. Let's start that simulation. And look at that. Now it's finally working. So with that, your ship's light simulation should be up and running. Tomorrow we will be showing you how to wire up to an external LED using a breadboard, wires, and also learning about resistors. That will take you one step closer to fixing the lights in your cabin. I know time is of the essence, but one step at a time. See you tomorrow.
Our hero board's LED is now blinking on and off every second. How spectacular! If you've followed all my instructions precisely, then you've just successfully completed the first part of your repair journey. You're one blink closer to seeing the inside of your mothership again. Now that you've got the board to successfully connect and run some rudimentary code, let's briefly go over what just happened in a bit more detail by taking a look at the code. All right, Explorer, we've uploaded our blink.ino sketch, and now we're going to decode it, much like how you might decipher alien glyphs. You'll notice grayed out text that doesn't appear to affect the sketch. Those are comments. They're like the sticky notes you leave yourself to remember why you decided to place a carbon dioxide scrubber next to the coffee machine. At the top of the Blink sketch is an example of a multi-line comment that begins with /* and ends with */, even if those characters are on another line. Anything between /* and */ is considered a comment and will be ignored when compiling or building the sketch. You could pen your magnum opus between these markers and the IDE would blissfully disregard it. Single-line comments start with a double slash and are used to add helpful notes or to temporarily disable a part of the code. Anything following double slash up to the end of the same line is also ignored by the compiler. Next, we have setup and loop, the synergistic pair of Arduino programming. You may think of them as the heart and lungs of your sketch, each equally essential with its own crucial role to play. The setup function sets up the variable, definitions, and initial tasks. It's a function that's run once and only once, when your program first starts. This is where you put all your preparations, initializations, pin mode declarations, and opening communications. So many ations. For instance, if we're using an LED, we need to tell the hero board that we've connected an LED to a particular pin and that it should be an output pin. This would go in the setup. To assist you in better understanding, please refer to this example. Now, loop is where, as you'd say, the magic happens. After setup finishes, the program jumps to loop, and as you might guess, this function loops over and over again for as long as your board is powered, repeatedly, forever. So, if you want to blink an LED, turning it on and off would happen inside the loop, like this. That's the basic purpose of the setup and loop functions. The former sets the stage, and the latter keeps the show running. All clear, Explorer? To explain the other functions, digital write is your digital switch. It can set a digital pin on your hero board to a specific state, either low, 0 volts, or high, 5 volts. Think of it as an on-off switch. The syntax for the digital write function is straightforward. Digital write, parenthesis, pin, comma, value, end parenthesis. Pin is the number of the pin you want to control, and value is either high or low. So, if you want to turn the LED connected to pin 12 on, you'd write digital write parenthesis, 12, comma, high, end parenthesis. To turn it off, you'd write digital write parenthesis, 12, comma, low, end parenthesis. You might notice that in that example Blink sketch, it doesn't use a number for the pin. We'll discuss a bit more about that tomorrow, but for today, just know that when you configure a board in the Arduino IDE, there are some names defined for you. In this case, LED_built-in is defined in the Arduino IDE as 13, which is the pin that the built-in LED is controlled by. Next, the delay function does just what an observant explorer would expect. It delays execution before continuing on to the next statement. The delay is for a specified period of milliseconds, which is 1/1000th of a second. If you want the program to do nothing for a second, you'd write delay, parenthesis, 1000, n parenthesis, semicolon, since 1000 milliseconds equals 1 second. In the context of blinking an LED, digital write is used to turn the LED on or off, and delay is used to control the length of time the LED stays on or off. Together, they create the perfect blinking effect. Aha! Starting to see the light, are we? Well, at least half the time. For your benefit, let's turn to some instructional material that I was miraculously able to gather cached on the computer. I've also added this to our mission resources for future reference. You're welcome. Well, well, Explorer, you've managed to make a tiny light blink. How terribly impressive. The interstellar community is no doubt holding its breath in awe. But please, let's not forget the minor detail that you are sitting in abysmal darkness, 60 meters under an alien sea while your rapidly dwindling oxygen supply bubbles away. It's imperative that we restore that battery charging system in order to extend your oxygen supply and buy us some time. Rest assured, every passing second I'm not working on saving your life, I'll be processing how we might avoid a similar fate the next time your curiosity gets the better of you. No pressure. It's only your invaluable life that is at stake. So, tuck yourself in, dear explorer. Dream of blinking LEDs and getting out of this mess you got yourself in. We'll need your brain fully operational tomorrow if we're to start getting your ship's systems back under control. Please, do try not to attract any attention, as I've detected some rather peculiar local sea life nearby. Sweet dreams.